The amines are bases just because really they're derivatives of ammonia. And if you remember, ammonia is a base. It's got a lone pair of electrons on here, which can be used to accept a proton. And remember, acids are proton donors, bases are proton acceptors. And ammonia accepts a proton by using the lone pair of electrons on the nitrogen. I'll just go through that over here. So there's ammonia, here's hydrochloric acid. So if this was a mechanism, I know it isn't, but you would get that taking the proton from hydrochloric acid, which then gives us NH4 plus on there, and then Cl minus over here. The amines are identical to this because essentially the amines are derivatives of ammonia. So if I was to replace one of the hydrogens with an alkyl group here, what I end up with over here is one less hydrogen and an R group in front over there. So they behave in exactly the same way. So we know, for example, that ammonia plus hydrochloric acid forms ammonium chloride. So CH3NH2, so that's methylamine, with hydrochloric acid will do exactly the same. So CH3NH3Cl, and of course the charges will cancel out, okay? So there's just some examples here really for you to have a look at while we're going through them. All right, so we've got methylamine reacting with hydrochloric acid, which gives the methylammonium chloride. Okay, if it was nitric acid instead, we'd have methylammonium, that's the iron nitrate. Okay. If we were using benzene, remember benzene, its name becomes secondary. So we've got phenylamine here with nitric acid, which gives the phenylammonium, and nitric acid forms nitrates. Okay. So all of these are forming the kind of alkyl ammonium chlorides all the way down here, which, as you've seen earlier, if you react it with sodium hydroxide, that's a stronger base, you will get the amine, NaCl and water, and that's always worth remembering. Okay. Now, in terms of the, and then there's some questions for you to have a go at there. In terms of the strengths of the acids, I've done this in the wrong order, but it doesn't really matter. In terms of the strength of the bases of these, it all comes down to the availability of the pair of electrons here. Remember, these donate to accept a proton, and proton acceptors are bases. So if these lone pair of electrons here are more readily available to accept a proton, it will be more basic. If they are less readily available to accept a proton, it will be less basic. And we've already had a look at the positive inductive effect when we were looking in the alkenes. Okay, so again, just to go back to this, let's use ammonia as our kind of standard. So here's ammonia, there's the lone pair of electrons which are being used to donate in order to accept a proton. Okay, so there's the proton there. Now, if one of these hydrogens is replaced with an alkyl group, so let's get rid of that one there. This is the one that we did in the alkenes. The alkyl group here has a positive inductive effect. It has a push of electrons away from it. That increases the electron density there, so it makes it more electron rich. And because it is more electron rich, it has a greater ability in order to be donated to accept a proton. So when we have alkyl groups on here, we have the positive inductive effect. The more alkyl groups we have on here, so if I put a second one on, the more alkyl groups that we have on here, the more positive inductive effect we have, which means the lone pair electrons on the nitrogen are more electron rich, or even more electron rich, which makes them even more readily available to be donated in order to accept a proton. Okay, let's go the other way. So let's get rid of the alkyl groups. Let's go back to ammonia. So ammonia is that, and is this. So if we have a positive inductive effect, it's reasonable to think that we will have groups that have a negative inductive effect, and benzene has a negative inductive effect. And when we do benzene and look at the structure of benzene, we'll have a look at what actually happens with that. So let me replace one of the hydrogens. Let me replace that hydrogen there with benzene. So I'll draw benzene. So there's benzene. And this now has a negative inductive effect. So it pulls electrons away from the nitrogen, which means the lone pair of electrons here are less electron rich, which makes them less readily available to accept a proton, which means it isn't as strong a base. So all that is outlined in here. So over here, when we've got benzene, we've got the negative inductive effect. Okay, and again, it's this bit here that I'll talk more about when we look at benzene. Okay, so that's the negative inductive effect. Every time you have an alkyl group over here, you have the positive inductive effect. And just like the Goldilocks story, when you've got ammonia, there's no positive or negative inductive effect. So that is our kind of baseline. And you can see here, look, that when we have the positive inductive effect, we have a stronger base, pH of 12, as opposed to 10. When we have the negative inductive effect, over here, we have a pH of 8. It's not as good a base. Okay, so from there, again, a few questions for you to have a go at.